between these? Maybe it's easier to start with what are the similarities? What do they do? They added hydrogen. What type of hydrogen did they actually add? They added hydride. How do we know it was hydride? Where was the hydrogen located in our final product? Where did it attach to?
The most substituted carbon.
I don't quite accept that. Just attached to that carbon, right? Where's that carbon in our starting material? Okay. A long pause. 1, 2, 3, 4. 1, 2, 3, 4. Worst case, we can say carbon number 2. Okay. Best case, we're saying it attached to the carbon of the carbonyl. Okay. If we're trying to identify what chemistry that hydrogen came in as, was it positive, was it negative, was it neutral, it can be helpful to look at where it reacted. It reacted at carbon number 2, and what do we know about carbon number 2? It is partially positive due to resonance. If it is partially positive, what charge does the hydrogen need to come in as? A negative, it's a hydride. Okay, no longer hydrogen, we need to refer to it as hydride. So they are both adding hydride. Okay? So that's how they're similar. What else could we say about them being similar? They're both attached to a cation. Good. Take that a step further. What kind of cation, Dana? Try that again. They're both group 1 metals. They both have a +1 charge. Right? Sodium and lithium are in the exact same column. Periodic table. What else is similar between them? We could reference they have an ionic bond. Okay, we kind of, it's a little, yeah, never mind. Metal and non-metal, both cases. So we do definitely have ionic bonds. Okay. What else do we have? What's a shared trait between boron and aluminum? Same column, which means? Similar reactivities. Okay. They're both connected to 4 hydrogens, right? Or rather, they're both connected to 4 hydrides. How do we know they're hydrides? This goes back to Laura's statement of it being an ionic bond. Okay. So now the question comes down is, what are those differences? Well, what is the difference between sodium and lithium?
Size.
How do you know it's just size?
They're molar masses.
They're in the same column. Size changes within a column. That's what we should be looking at, is size. How is that going to be important? Both of these reactions are going to produce an intermediate. A negatively charged oxygen, right? Okay, because as the hydride comes in, what could we do to stabilize that negatively charged oxygen? Okay, we could try and bring in the boron. What else could we bring in? A positively charged metal. Okay. Which of those metals is going to do a better job of stabilizing the negative charge? Okay. So we heard 2 answers. I heard lithium and the bigger one. Okay, so let's evaluate that a little bit closer. Is that the same answer? No. No. Okay, why would you say lithium? It's smaller, so it might be able to get a little bit closer. Okay, but can it stabilize that charge as well? Okay, probably not. The larger one is going to be able to share those electrons a little bit better. We'll probably get a better or stronger interaction between those. Okay, the lithium being smaller will get in real tight to it. Okay, which can change its aspect or change the stability of that negative charge. What else could we look at? How about the boron versus the aluminum? What's the difference there?
Electronegativity is a difference.
Okay, we have an electronegativity difference. We also have size difference. Okay. How is that going to help us? Or how does that affect the reactivity of the hydride? Where are the hydrogens attached? That didn't work. Hydrogens are attached to boron or the aluminum. Okay, how would electronegativity have an effect on that hydride? If the boron or the aluminum, whichever one of those atoms is less electronegative, what does that mean?
It's easier to give up the electron.
There's a larger difference between the aluminum and the hydride, making the hydride more and more negative, which then correlates back to reactivity. Okay? Aluminum being less electronegative then says that hydride becomes even more reactive. Okay? What else is the difference between boron and aluminum? Size. How is that relevant?
Stability.
What about the stability?
Stability of the charge.
Stability of what charge?
Like of a negative charge.
Where is the negative charge?
On aluminum, the negative charge, or in that,
Negative charge is on the hydrogen. If we move to a bigger atom, what happens to the bond distance between aluminum and hydrogen?
it gets further away.
It gets further away, which makes the hydride more reactive. Okay? So if we compare the reactivities between these, the lithium aluminum hydride is significantly more reactive. Okay? And we can evaluate it by looking at the atom effects all the way through it. The other thing we can do, what else is another big difference between these? How many steps? Sodium borohydride is done in one step. Lithium aluminum hydride is done in two. Okay. What is the solvent for sodium borohydride? Water. What can you tell me about water as a solvent? I think I heard it that I would accept. I heard acidic. It's a little bit overstated there. It is polar protic, so it does have the potential for acidic hydrogens. Is that going to become relevant if I've got a solution full of hydrides? What is hydride going to do? It's going to react with positively charged species. If I have an acidic solvent, what's going to happen? It's going to quench the hydride. Yet when we look at sodium borohydride, do we care? I wonder why we don't care. Because the sodium borohydride is not as reactive. Right? Because it is less reactive, I can get away with a solvent like water. What happens when I look at lithium aluminum hydride? What is my solvent there? Ether. Good. Nobody said H+. Ether. What can we tell me about the ether? It is polar. Why would it need to be polar? To dissolve the ionic compound, but it is polar aprotic. Why do I want to make sure there's no acidic hydrogens?
Because those hydrides are very reactive.
Because the hydrides in lithium aluminum hydride are that much more reactive that if I had a protic solvent, what are those hydrides going to do? React with the solvent into an acid-base reaction, not act as nucleophiles. Okay. Notice with the lithium aluminum hydride, I have a second step of adding H3O+. Sodium borohydride, I didn't add H3O+. And yet somehow I'm still getting a hydrogen on my alcohol at the end. How did I get the hydrogen on the alcohol for sodium borohydride? Got it from the water. Where did I get the hydrogen in lithium aluminum hydride? I have to add a proton source. Okay, that's the H3O+. Why was it not added as one step? It would just turn into H2 gas. I would get the acid-base reaction, not the nucleophile reaction. Kind of makes sense? So we have two primary reagents to adding hydrogen, or adding hydrides. Okay? And they will do a nucleophilic addition. You take the nucleophile, you jam it up the electrophile's carbonyl. Sorry. That went south really fast. That didn't get any better. Screw it. So if we look at our reagent conditions, okay, that's what this slide is now evaluating. The lithium aluminum hydride will react very, very quickly with a protic solvent, okay, and we end up forming the hydrogen gas. The sodium borohydride will react very, very slowly. So it does react to form hydrogen gas, but that reaction is so slow that what happens? I can get the hydrogens to react as nucleophiles before I worry about losing them to the solvent. Okay? Could I have done sodium borohydride in ether instead of lithium aluminum, or like lithium aluminum hydride, instead of using water? Yeah. Why not? Why did I use water and not, say, an ether solvent?
You would have to protonate it at the end.
So we could still protonate it at the end. Ether is a volatile, toxic, organic chemical. Water is not. Okay? We can choose our solvents with that kind of green chemistry ideal in mind, using the minimally reactive necessary to do our reaction. Okay? So if we take a look at our nucleophilic additions, okay, our primary driving force was carbonyls. Okay, but really what we're reacting is not carbonyls, we're reacting hydrogens or hydrides, but with what? Carbons. Okay, why is the alkene not shown up here as my list? Why does that not work for this reaction? What do all of those carbonyls, oh wait, they aren't all carbonyls. What do all of those pi bonds have in common that is not in common with an alkene? Won't quite accept lone pairs.
Differences in electronegativity?
Differences in electronegativity. We have oxygen versus carbon. What's the difference? Oxygen is more electronegative, making that pi bond polar. Polar, 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 polar. Touche. The alkene, not polar. Okay, so one of the things we have to remember when we're looking at this chapter is, yes, we're looking at carbonyls as our primary functional group, but are imines, I don't expect you to know that yet, are imines polar pi bonds? Yeah. Are nitriles? Yeah. For those of you struggling with the online homework, okay, what's a challenge with our nitriles? How are they typically written out? CN. So when I look at that compound, I really have this. And when I look at CN, what's the issue? There's an implied, in fact, two implied polar pi bonds, okay, that are buried in the information. You have to be able to convert your structural formula into line formulas. You have to remember those things are hidden in there, just like our hydrogens. Okay. What does this mean as far as our nucleophilic addition reactions go? Okay. Would I expect the same reactivity for every single one of these carbonyls? Okay. What's different about them? What's that? Okay, so substitution. If we're going to look at a substitution pattern, we can kind of look through the middle there. How is that going to have an effect? Sterics. Okay. I'm trying to put a hydride, albeit hydrides are relatively small, but remember they're attached to the lithium aluminum or the borohydride. And I'm trying to do a backside, sort of backside, entry into that pi bond. Right? Am I going to run into an issue in any one of those three cases?
Yeah.
The last one has R groups with more electrons, which will do what? Repel the attacking hydride, which means slower and
Less likely.
faster. Okay. What else do we see as a difference? Okay, which ones are you looking at? Okay, you're comparing that halogen. What do you want to compare it to?
The slope. That guy.
Anybody want to help Sean out? Ketone, thank you. Okay, we have the ketone function group. Between those two, which of those should react faster? Why should the chloride react faster than the ketone? Chlorine is electronegative, withdraws the electron density, doing what to that carbon? Making it even more electrophilic, which means it should react faster still. All right, what else do we see as a difference? We have nitrogen coming in now. What's our differential there? Electronegativity. How is that going to affect our reaction? What do you mean slow it? Elaborate.
It's more electronegative, so it's holding on to its electrons.
Which is more electronegative?
The nitrogen.
Nitrogen versus oxygen. Nitrogen is
Oh, we're
less
comparing the
electronegative.
oxygen.
Nitrogen is less electronegative, meaning it's holding on to its electrons less tightly, which does what to the polar pi bond? Makes it less polar, which makes it less reactive still. Okay? So it's trying to recognize and find these patterns. We could even drop all the way down to the triple bond, and I would argue the nitrile is a tricky one to deal with, which you may have seen in the video that I recorded, but I don't remember. BH4, our sodium borohydride, we'll do all of those. Lithium aluminum hydride, we'll do them all. Okay? And it has to do something with their reactivities. Okay? The triple bond is not quite reactive enough for sodium borohydride to react with it. Lithium aluminum hydride, being stupidly reactive, will react with anything with a polar pi bond. Okay? Selective, not selective. Okay? If we drop that term into it, selective versus non-selective, which should be our go-to reagent? The selective one, okay? Our borohydride, because that will give us better results because it's targeting a functional group as opposed to hitting everything that it sees. Okay? As a preview into chapter 20, okay, let's take a look at these three compounds. What are the names of each of these functional groups? And I'm not going to let Sean redeem himself. Sorry. You're welcome. You can redeem yourself on one of the others, but not the first one. Anybody got names? What are the functional groups?
Ketone.
Not an ether.
Ester.
Ester. Acyl chloride. And Sean, you are valid as well. And acid chloride. Not the chlorocarbon. That's an alkyl halide. But calling it an acid chloride works as well. Okay. What is the big difference that the last two bring into this argument? What is different about those last two from the first one?
More induction.
Start to reference an inductive effect. Okay, we'll find out that's going to be a bit misleading. Okay, if it starts to withdraw those electrons, more positive is saying inductive. If it starts to withdraw those electrons, what are we doing? What do we have? Say that louder. We have a leaving group potential in those last two. Do we have a leaving group in the ketone? No. So what happens when we react the ester with an acid? Or sorry, with, say, lithium aluminum hydride? We would end up doing a substitution. What is the issue now with this structure? Is it an ester anymore? No, it is an aldehyde. How do aldehydes react in the presence of lithium aluminum hydride? Faster than esters. Which means the first product we get when reacting our carbonyl compounds with leaving groups with our lithium aluminum hydrides generates a more reactive structure, which means it keeps reacting.
So you probably end up with like a...
So what would we end up with? It reacts a second time to add a second hydrogen. We permanently, oh man, that was supposed to erase nicely. We would permanently lose the pi bond. We'd end up with our negative charge, and we'd follow this up with our acid, and we would end, whoa. My eraser, oh, never mind, I see why. we would end up with our primary alcohol. Interesting. Okay? By recognizing what things are present and how those structural effects change the chemistry, we can start to predict something about something we actually have no concept of. We have not talked about that type of reaction yet. Okay? And yet you're able to recognize and predict those potentials. Okay? That is an important skill from this class. So we've got a little bit of practice here. 4 questions. I want 4 answers. Color that in red. You can talk to the people around you. So we've got 3 products and 1 reactant. See what you can come up with. If you got questions, raise your hand. With our hydride nucleophile, that first one could be put on a test, written as is. A, B, C, or D. What's our answer? C. Okay. We may run under the tendency of saying, well, it's A because I had lithium aluminum hydride, and hydride reacts with my carbonyl to reduce it. Except the acid is being added at the exact same instant. Okay. If the acid is added at the same instant, the acid is more reactive than the carbonyl. Lithium aluminum hydride reacts with the acid. We no longer have a hydride nucleophile, which means nothing happens to the carbonyl, and we end up with C. What happens if we split it into 2 steps? Now we could get A as our answer. Okay. The hydride has nothing else to react with other than the carbonyl, so it will do its standard reaction. Okay. What we had for 3, it's just doing the reduction. We just turn the carbonyl into an alcohol. That's it. 4, we're doing the reverse. Our hydride reagents make alcohols from carbonyls. Turn it into a carbonyl. Simple as that. Okay. How would I have gotten an extra methyl there? What would that have changed? It would have had to have been a secondary alcohol. All we're reacting is the carbonyl carbon. Okay. Everything else needs to stay the same. So don't change it. Make sense?
So the absence of or the changing of the benzene ring to cyclohexane doesn't have an effect on...
Nope. So why did I put the benzene ring versus the cyclohexane?
Just to screw with us?
Just to screw with you, because you have this nasty habit of looking at that structure and saying, oh, that structure's got to do something. No, it doesn't. Okay. Identify your reagent, what it reacts with, and do that. Okay. Keep your focus on where that chemistry is occurring. Which gets us to the next part, carbon nucleophiles, which splits into 2 sections. We've got the Grignard reagent and the Wittig reagent. Okay, the Grignard reagent, I would argue, is a nice, straightforward, simple one. The Wittig reagent is a real SOB. I'm hoping to get to it, okay, because we need to catch up. Okay. So let's take a look at carbon nucleophiles. We've made carbon nucleophiles before. Okay, what carbon nucleophiles have we seen? Have we actually made? Made versus used. There have been a couple times where we've used carbon nucleophiles, but we haven't made them. Okay. But we've definitely made carbon nucleophiles. Lab on Monday, that's Grignard, so let's ignore the lab for the moment. Where should we start?
With an ionic bond?
How about with carbon? Okay. How about if I add a hydrogen to that carbon? And I add another carbon and another hydrogen? Maybe that's kind of confusing to look at. What was special about our alkynes? They were acidic. We can deprotonate them with a really strong base, and we end up with a carbon nucleophile. Back to Tyler's statement, said something about ionic bonds. What else is produced? Ammonia gas, I don't care about the ammonia, and what type of bond do we have here? an ionic bond between a metal and carbon. And that got us carbon nucleophile. Hey, that was cool. Where else have we seen carbon nucleophiles? What's that? Enolates. Okay. How did we form our enolate? What did we add? Typically added a base, and it did what? Our base needed to be strong, so let's do sodium hydride. We produce hydride and our enolate with which has an ionic bond, a metal and carbon. Cool. We have one more that we've seen for sure. This one you may not think we've made, which might be a valid argument. What do we have here? Cyanuric acid, I think. What can we react with an acid? How about a base? What happens when we react that with a base? What do we get? H2O and... Oof. Clean that up a little bit. An ionic bond! Carbon bound to a metal. If we can get carbon bound to a metal, we've got a carbon nucleophile. Okay? What did we take advantage of in all three of those cases? Acid-base chemistry. Okay? Fun thing about acid-base chemistry is that it's boring, which means easy. No one can attach their name to those reactions because it was stupidly easy. You just added a base. That doesn't count. You got to do something cool. Okay? This is where Grignard comes into the play. Okay? It is not easy chemistry to go through and do. Okay? We have to change something about the carbon nature to make it acidic in those cases because it's too small and unelectronegative to allow it to hold a negative charge. So we looked at resonance, we looked at hybridization, okay? We looked at an inductive effect for all three of those, trying to find ways to stabilize that negative carbon. Okay? For it to become negative, I needed a metal somehow in there. And in all three of those cases, the metal did nothing. It was a spectator ion that just kind of balanced us out. Okay? So let's think back to all the reactions we've done this semester and last semester and think of all the times that metals were used as actual reagents. Well, there was... No, that wasn't a metal. No, that wasn't a metal. No, that wasn't a metal. How many times have we used metals to act as a reagent? Once? There was one?
Monday.
Stop talking about that. Okay. We have what are known as your organometallic ions, so organic materials, carbon-containing, with metals. Okay. There are two primary big categories that are new to us here. We have the Grignard reagent, and we have the organolithium materials. Both of them work by inserting the metal next to the carbon. If we take a look at the Grignard reagent, it's the one on the left, because it's the one without the lithium, right? Sort of a joke. We start with an alkyl halide, and we add magnesium. What is special about that magnesium? What is the charge on that magnesium? Nope. How do you know it's neutral? There is no charge indicated. Remember, we can never assume charge. It must be supplied. So if there's no charge specified, there is no charge. That is neutral magnesium. That is magnesium metal. What is special about magnesium metal? Why is it reactive?
Because it can easily give up electrons.
It can easily give up 2 electrons to become
2+.
magnesium 2+. What is the charge of magnesium in our product? How do you know it's 2+? It's lower in electronegativity than both the carbon and the bromine, meaning it gives up its electrons to make those bonds. Neat. What do we have as a characteristic for our lithium? It can give up what? one electron. That's it, one electron. It can dump one electron out, and in the process, it can insert itself, and we can form your organolithium compound. In all cases, those reagents in red are special because they are carbon nucleophiles. Once we have the carbon nucleophile, we can now do all sorts of crazy fun stuff with it. Okay, so let's take a look at some of those things. These tend to be very rare, useful, and tricky to form. Okay, those of you in lab, how easy was it to make the Grignard? Let's see what your opinions are of that whole process.
Well, you did most of the work, so it's pretty easy.
Yeah, okay, so those of you who are not in the lab, okay, they went through and made a Grignard reagent with me panically running around, pumping needles and shoving nitrogen and removing water. Okay, why would we remove water? What would we say was the issue with water?
It would probably
So reactive and reactive.
Why is water reactive? Water could act as a nucleophile, but our Grignard is supposed to act as a nucleophile. So a nucleophile doesn't do anything. Could water act as an electrophile? It can't accept more electrons.
It could act as an acid.
It could act as an acid. What's a characteristic of all nucleophiles?
They're a base.
They are all negatively charged, and negatively charged species often act as bases. So when we think back to our Grignard reagents and the organolithiums, why are they exceedingly rare? Carbon is small, and carbon is not electronegative. Okay? Which means it is not easy to make them negative. Why are they useful? I can now make a larger carbon structure. Because I can connect one carbon to another carbon. I got tons of carbon electrophiles. I don't have a whole lot of carbon nucleophiles. Okay? So I can build much larger structures using carbon nucleophiles with my Grignards. Why are they tricky reagents to work with? They are highly reactive as both nucleophiles and as bases. So because it is a nucleophile, it is useful. Because it is a base, it is a tricky reagent to work with. Okay? So, let's take a look at the actual formation reaction. And before you start panicking and drawing this out, you are not officially responsible for this in the lecture. Those of you in the lab might want to actually take notes. Okay. Where's our Grignard reagent?
The end?
The end is our Grignard reagent. Grignard. There it is. Okay. And we're starting with what? An alkyl halide. In this case, we're starting with a benzene, a bromobenzene, but it doesn't have to be any. It doesn't have to be bromobenzene. It can be any alkyl halide. Okay. What is the charge on the carbon in your Grignard reagent? Why are you saying partially negative? Bond to what? What can you tell me about the bond to magnesium? It's an ionic bond, which then means, really, I shouldn't even be showing it. What I should be looking at would be, and what is the characteristic of our carbon? It's not partially negative, it is pretty much as close as we can possibly get to formally negative. Okay. What can you tell me about the carbon in the alkyl halide? Partially positive. This is interesting. We're going from a positive carbon to making it full-on negative. This is what's known as an Umpelong synthesis, which we'll talk about at the end of the semester. Umpelong meaning, I think it's German, change. What are we changing?
Charge.
The charge. By changing the charge on the atom, we're doing an Umpelong synthesis. Just a fancy word for it. Don't ask me to spell that, I can't. Okay. That's why it's on the slide somewhere. So somehow or another we have to get the positive to become a negative. What does our magnesium do? Well, the magnesium supplies electrons, and it is desperate to ditch those electrons. Okay? Which electron do you think is going to be reactive in that first step? It's kind of a pseudo-dick question. Which one?
The green.
I'll accept green. Not the red one. Why not the red one? Look at the product. The product has the red one still, which means has to be the blue magnesium arrow. So that has to somehow ditch its electron. What's it doing to the other one? Nothing. It holds it. Which means what type of mechanism are we doing? A radical reaction. Okay? Something needs to react with that magnesium. What is that something? Okay, if we look at our result, something about the bromine is now reacting. Okay, and as you're pointing out, it's the bond between the carbon and the bromine. We're taking the electron from that bond, and bromine saying, I'll actually share that with the magnesium, not with the carbon. But what happened to the last electron then? Didn't go anywhere. It's still stuck to the carbon. The result is we form that radical benzene structure. What do we know about radicals? Very reactive. What is that radical going to immediately try and do? Find another radical, and we end up with our Grignard reagent, where the magnesium is now inserted between the carbon and the bromine. How do we know this mechanism is valid? Because we can observe the formation of this structure. If we did not go through the single electron transfer pathway, that product doesn't exist. Because that product exists, the only way we can get it is by doing a single electron transfer. Okay? You should be able to theoretically predict and do the arrow pushing for that, but I'll leave you to do that. Whoa, that was a bit, whew. So let's slow that down. Okay. Once we have the Grignard reagent, which is really all you're going to be responsible for doing, is looking at your structure and saying, oh, I have a Grignard reagent. Okay, when do I have a Grignard reagent?
Ionic bond to
Is that a Grignard reagent? How do we know? Is that a Grignard reagent? Yes. Okay. So what you should do as soon as you see that metal bond is erase it. If you got a whiteboard, this is one of the awesome reasons for a whiteboard. And draw a negative charge. We now know that that carbon is going to be acting as a nucleophile. What do we need to find? An electrophile. So what if we react it with formaldehyde? The nucleophile comes in and attacks the carbonyl carbon. That breaks the pi bond, and we form the negatively charged oxygen. Okay. Is that reaction going to be a good reaction to occur? That very first step. Would we expect to form negatively charged oxygens in solution? No, why? Huh?
It wouldn't stay that
I can kind of accept it wouldn't stay that way. Where have we said no to negatively charged oxygens before? How about hydroxide leaving groups? Said those were bad. What do we effectively have here? Kind of like a hydroxide leaving group. Why is it okay? Look at the environment it's leaving into. We produce O minus, and we started with C minus, which is more stable. O minus. Hydroxide is not a problem at all, because that is more stable than the negative carbon. That reaction is not very reversible. Okay? We're looking at driving primarily to that intermediate or that product structure. The issue with that product structure is that it is negatively charged. Okay, so it needs to be stabilized. Is there something positive floating around in solution that could stabilize it? No, not really. So what happens? Nothing happens. The reaction stalls. What do? We decide it's reacted long enough, and we say, stop reacting. And we do that by perhaps doing a second thing, like a second step, and adding. Don't all shout it out at once. An acid. Why add an acid? What are we trying to quench? We're trying to quench that negative oxygen with a positive atom. Our acid will add that positive hydrogen. And we end up with what type of an alcohol? We have an alcohol that is attached to a carbon that is connected to one other carbon, and we have exactly what I heard, I think you said, Maddie, a primary alcohol. What happens if instead of reacting with formaldehyde, I switched it up to aldehyde? What am I going to end up with? A secondary. There's now an extra carbon there. Okay? And let's not show the answer. What happens if I start with a ketone?
Tertiary?
There it is. Way to jump out on a limb. We have the tertiary alcohol. Okay? Is that reaction going to go slower? Possibly. Okay? But before we start freaking out about the sterics, what is the thing that we need to be looking at? Carbon negative versus oxygen negative. Which is more stable? The oxygen negative. That reaction is going to overwhelm virtually any activation barrier. Okay? So we can form varying substitutions of our alcohols. So there we go. Fun little practice. Answers are up there. First one, standard Grignard reaction. Nothing fancy about it. The negative carbon attacks our carbonyl. And we'd add, it's a good thing I didn't actually add the methyl group. So let me fix that. There's the methyl group. Ta-da. Okay. And first one should be good. Theory, everybody should have gotten that. If you didn't, you need practice. That's fine. You just need to practice on what's going on with these individual reactions. The next one down. What happened to the next one down? Nothing. How did that happen? So a couple people pointed it out, but then didn't do anything with it. We have a phenol, which happens to be acidic. The Grignard reagent reacts with the alcohol, or reacts with the acid, deprotonates it, followed by step 2, puts the hydrogen right back. Nothing happens. Okay? Last one, or the far right. Okay? CO2, everybody looks at that and freaks out and says, I have no idea what's going on with it. Maybe it would help if you drew the structure. What does CO2 have? 2 double bonds. The negative can come in and attack, and we end up with a carboxylic acid. Okay? The last two end up getting tricky, or sort of tricky. We'll do the bottom left first. We have a nucleophile. We have that polar pi bond. It can come in and attack. It breaks one of them. It can't break the second. Why can it not break the second one? Because this is the intermediate. I can't do another Grignard attack because I'd be making that nitrogen even more negative. That negative prevents the second nucleophilic attack. Okay, so it kills it there. I then follow that up with the acid addition with the hydrogen. For the last reaction, what happened? Again, nothing. Why? That hydrogen is likely still too acidic, and it's going to react with the Grignard. If I wanted that nucleophilic attack to happen, what do I need to do? Turn that hydrogen into a carbon. Okay. Now what would happen? Now I can get my nucleophilic attack. Okay? So we have to be careful with our reagents, how they interact and how they flip and convert on you. If you have questions, that's sort of rage. Sorry. Okay? We will come back to this one. Take a look at these. Straight from your book. The top ones are good. The bottom ones are bad. We'll start Monday. Yes, Monday with the explanation. I want to know why the top ones are good, why the top ones are bad. Might actually be easier for your quiz to just pick one of the bottom ones and say that's why this one is bad. Okay, that's probably the easiest approach. The last thing that I'll talk about before we completely leave, the Wittig reagent. This is our Wittig reaction. We start with a halide, okay, an alkyl halide, and what's our end result? We end up with an alkene and more carbons. We expanded the carbon structure. What does that mean? We somehow generated a carbon nucleophile. How? Through that big cluster stuff of reagents in the middle, through a bunch of ugly, nasty things that are all kind of cool but difficult to remember. Okay? That is our Wittig reagent. That's pretty much the last big section out of this chapter. The next part is our conjugate additions, and we'll continue through that probably next Monday. We'll be into chapter 18 no later than Wednesday.